Okay, so in this video, this is the second one in our series looking at carboxylic acids, and in this video we're going to be looking at the preparation of carboxylic acids, and we're going to start to look at some of the reactions of the carboxylic acids. So you're going to need your notes, and we're going to be looking at page 5. Okay, so we're on page 5 of your notes, and we're looking at the ways of making carboxylic acids. Now there are actually 6 possible ways to make them, so there's quite a lot of different ways that you can actually make a carboxylic acid. Several of these you've already come across before. The first two, for example, oxidation of an aldehyde and the oxidation of a primary alcohol. So we can oxidize ethanal to ethanoic acid, nice and straightforward. So we've got our ethanal molecule, and I'm just going to let O in brackets stand for my oxidizing agent, because there's a variety of things that can do this reaction, and that's just going to basically turn it into my carboxylic acid. So that's a nice one you've come across before. You've also come across this one before, where you do the primary alcohol, in this case ethanol, and you would heat this under reflux with your oxidizing agent. In this case it would usually be potassium dichromate in sulfuric acid, but again you would make your carboxylic acid, and those are two you've seen many times before. This next one you haven't seen a lot of, but you have actually seen it in the carbonars pack, and this is the hydrolysis of a nitrile. Hydrolysis just basically means breaking up with water. So hydro, water, lys, break. Our reagents are actually dilute hydrochloric acid, because this reaction does work with water, but it's just incredibly slow. So we do what we call acid hydrolysis, which basically puts in some hydrogen ions as our catalyst. So dilute hydrochloric acid, which is water plus my acid catalyst, and I'm going to heat this under reflux. So I'm going to take ethane nitrile, my 2 carbons with my triple bond nitrogen on the end, and I'm basically going to add some water to this. And as I said, this is done under acidic conditions, because otherwise it's too slow. And I get my product, which is my carboxylic acid, and I get ammonia as a separate product. Or with the acid present, I would probably get ammonium chloride, NH4Cl. I've got a lot of HCl knocking around the place. Not only can I do an acid hydrolysis, I could also do an alkali hydrolysis, where in this case it is the alkali ion which is acting as the catalyst. I've still got my water. Now because I've got an alkali present, I'm going to end up with the salt, the ethanoate ion, so then I would have a second step here to add some acid to turn it back into the free carboxylic acid. Okay, so this works with all nitrile compounds. So for example, this one, which is a hydroxynitrile, again I could react it with dilute acid. So I'm going to get my hydroxy. The OH group isn't going to change because I've got no reaction between that and the acid. I'm just going to add the acid in this time, and I'm going to get this time a hydroxy carboxylic acid, and I'm going to get my ammonium chloride, NH4Cl. Okay, so the last couple are ones that you possibly haven't seen before. The first of these is the hydrolysis of an amide. This is very similar to the hydrolysis of a nitrile. We're still going to use dilute hydrochloric acid, and we're going to use water to split it up. The acid is just the catalyst. So we're going to take our ethan amide. It's not a molecule you've come across yet, but you will do later on. And we'll study this again as a separate topic in the second year. So this is an amide. It's got a C double bond O and this NH2 group. and I'm going to add some water to it. I'm going to need to do it under acidic conditions because this is acid hydrolysis. And I'm going to get my NH3 and I'm going to get my carboxylic acid. Like that. Okay. Hydrolysis of an ester, we're going to look at that later on in this pack, but that's another way that I can make a carboxylic acid. Last but not least, one that a lot of people forget is the iodoform reaction. Now the iodoform reaction is usually there to test for either an OH group or a C double bond O group adjacent to a methyl group. But you have to remember that the organic product is always a carboxylic acid salt in this case, with one less carbon on it. So it's quite a useful little reaction to know. It's quite difficult to balance it, so I'm afraid it's one of these ones you are just going to have to learn. So I'm going to take propan 2-ol, which is one of my molecules which will give you a positive iodoform test because it's got a methyl group adjacent to this carbon with the OH group on it. And I'm going to add iodine, and I'm going to add some sodium hydroxide, and I'm going to make my CHI3. That's my triiodomethane, that's my yellow precipitate. I'm going to get some water. I'm also going to get some sodium iodide, and this is the important bit in this case, I'm also going to get a carboxylic acid salt with one less carbon on it. So I've gone from a prop here to an eth here. If I now added a little bit of acid to this, I could get ethanoic acid to be produced. Okay, so we're looking at the first of the reactions of the carboxylic acids, and this is related to their acidity. So they undergo typical acid-base reactions. So they react with hydroxides, carbonates, and hydrogen carbonates. So we're just going to look at those three reactions. So propanoic acid, we've got 3 carbons, and I've got my OH group. And it's that OH group that's important because it's that hydrogen ion that I'm going to lose, and I'm going to add potassium hydroxide to this, and this is a simple acid-base reaction, so we get water and a salt. In this case we get the propanoate salt. So I got my carbons, double bond oxygen, this oxygen has lost the hydrogen and it's now got that ionic bond between them. Methanoic acid, where you've got your methanoic part, and I'm going to react that with some sodium carbonate, Na2CO3, and it's going to produce your usual carbon dioxide and water, and you're also going to get your HCO negative, Na positive. In order to get it to balance, I'm going to have 2 of these and 2 of these. Okay. Last but not least, ethanoic acid and sodium hydrogen carbonate. Well, again, we've got our ethanoic acid. Drawing these all out displayed, but you don't have to draw them displayed. You can draw them as skeletal or structural if you want to. NaHCO3, and again, you get the same carbon dioxide and water, and you get your salt. So you've got C, double bond O, O negative, Na positive. Very nice and straightforward and very easy to balance. Okay, so these carboxylic acids are what we call weak acids when compared to things like nitric, sulfuric and hydrochloric acids. Weak and strong has nothing to do with concentration, it's to do with the amount of dissociation, how easily they give up a hydrogen ion. Now don't worry about that at the moment because acids and bases form a topic in the second year, so we're going to study that in much more detail later on. But we do need to understand that our carboxylic acids dissociate in water to release the hydrogen ion, That's what this looks like. That's basically a water molecule which has accepted a hydrogen ion and to leave behind the salts. They're weak acids, and that means that this position of equilibrium lies well over to this side. Okay, but when we look at the carboxylic acid ion in more detail, the carboxylic ion, we would expect, looking at these bonds, we would have a double bond and a single bond, and this double bond would be shorter than this single bond. But actually, when we measure the bond lengths using X-ray diffraction, we find that the bonds are all the same length. So they're shorter than a single bond, but they're longer than a double bond. They're kind of an intermediate shaped bond. And that means that this negative charge, we say it's delocalized across this group. So across this oxygen, carbon, oxygen, that negative charge is delocalized. It's spread out. Now, because it's spread out, it's much less attractive to the hydrogen ions, and they're much less likely then to join back on. It's a much more stable ion, and it's much less likely to be pronated. And that is why they're considered acidic, but the alcohols are not. So in carboxylic acids, this negative charge is delocalized over the whole of this group. So we've got this spreading out, this smudging of these electrons, and therefore the hydrogen ions are not likely to be attracted back to it. Whereas if we've got an alcohol functional group, there's nowhere for that negative charge to go. So even if I could break that oxygen-hydrogen bond and get that oxygen on its own, that hydrogen ion would stick back on almost immediately, and we'd be back to our alcohol functional group. So that would happen pretty much instantaneously. Whereas here, because that negative ion is delocalized, it's not as attractive to that hydrogen ion, and it doesn't join back on as readily. Okay, so the last reaction we're going to be looking at is the reduction reaction of carboxylic acids. And we're going to use our usual reducing agent for this, lithium aluminium hydride, LiAlH4, and we are doing this in dry ether. Okay, and initially, again, we've got this LiAlH4, which is a source of hydrogen negative ions, and they're going to be attracted to the delta positive carbon of the carboxylic acid functional group. So we're going to take ethanoic acid. Now this is a very powerful reducing agent, so I can't get it to stop at the aldehyde stage. It'll go straight back to my ethanol. So it'll go straight back to here. You don't get any aldehyde being produced because it's too strong. It'll go straight to the alcohol phase. It won't stop at the aldehyde. And I'll also get some water. Okay, so basically that's my reduction reaction, and so I can oxidize my primary alcohol to an aldehyde and then to a carboxylic acid, and that is all oxidation. So in that direction we're doing oxidation, and in the reverse reactor direction, so going backwards, we're doing reduction. So oxidation going forwards, reduction going backwards. Okay, so that just finishes this section of the notes looking at the preparation of the carboxylic acids and their reactions. In the next section, we're going to be looking at the practical and how we test for an OH group and some of the typical reactions of the carboxylic acids. So until then, take care, stay safe, bye bye.